In the third and last part of the section, we'll consider nonlinear variants of the supported vector machine classifier. The reason why supported vector machines are quite popular among machine learning practitioners is that it can be easily kernelized to solve nonlinear classification problems, incorporating inseparable data sets. The basic idea behind the kernel method is to transform the data point into a higher dimensional space. Let's see this figure. Now we have points in two-dimensional space, and one class is given in this way, and another class the surrounding the other class points. Then any linear classifier is not effective to classify this data set. Now we try to transform this data set into three-dimensional space by adding one more component, which is length squared. Then you can see, as in the figure, now outer point will go up in the z direction, and now inner points will go down. So you can use the linear supported vector machine to separate these two groups of data points. Then once you try to look at this separation into two-dimensional area, then you can see this one. So it is a good separation classification. That's the idea of kernel method. Okay, here we have a little bit of expression. And first we transform the data points onto a higher dimensional feature space by using a mapping phi, and train a linear supported vector machine model to classify the data in this new feature space. Then now use the same mapping function phi to transform new and unseen data point to classify it using the same linear supported vector machine model. So that's the idea of kernel supported vector machine. Now, however, explicit expansion of the dimension is cumbersome and also time consuming. So we need a little bit of a trick. So in order to make a trick, let's recall the problem. For the linear supported vector machine, in fact, for the soft margin supported vector machine, the dual problem is formulated in this way. So mean part is solved by using KKT conditions, and we can form this objective and as a function of Lagrange multipliers. Now that's the problem we have to solve. Okay, now here, this one is involving xi, xj dot product. So once we consider the future expansion onto a higher dimensional space, then, and anyway, after expansion, we have to make a dot product in the same way. So this one, once you are considering kernel SVM, then this dot product will be replaced by this one. But anyway, this is a scalar depending on xi and xj. So rather than we are making explicit expansion and dot product, okay, we may try to introduce a function which is called the kernel function, such that it is an approximation or a good representation of the dot product. anyway, this expansion is a nonlinear expansion from xi, and also this one is, again, an expansion from xj. So this function, if this kernel function includes everything for the operation, then instead of explicit extension, we can make a scalar for xi and xj. That is the basic idea of kernel tree. Okay, so we can find some kernel functions. It is a radial basis function, or sometimes it's called the Gaussian kernel. And between xi and xj, we measure the quantity through this function. And anyway, now originally this dot product is a kind of a similarity measure. Once they are orthogonal in a very different direction, then the value is around 0. And once it is the same direction, then the value is now large. And once opposite direction, the value will be negative value. Anyway, this original dot product is a kind of a similarity measure. And after expansion, again, now the dot product must be measured. Again, this must be a kind of a similarity measure. And this function, and quite easily you can see that this function is a kind of a similarity measure. Okay. Okay, so that is the idea of kernel tree. And rather than explicit expansion, just we try to approximate or try to find a good representation, meaningful representation of phi xi, phi xj dot product. Here we have common kernels, and there is a polynomial of degree exactly k. For example, when k is 2, now xi dot xj and square, and many other k can be chosen. But if you are choosing higher k, then it's not really working effectively. So that good choice is around 2. And also, you can make a polynomial of degree up to some k. Now, so that by adding here a constant, you can make this as polynomial of degree k. And also, you can use this hyperbolic tangent function and for the kernel function. And now we consider this one, Gaussian kernel. Okay, also there are many other kernels, Fisher kernel, graph kernel, and string kernel. And yet, this area is an active research area. Let's see this example, quadratic kernel. And once we consider this function, a constant plus and this dot product squared, then using some algebra, we can reach out these terms. But if we define the expansion and a phi function from x to 1 to xm, and in this way, then in fact, these final terms can be the same as phi x dot phi z. So that this simple function, and if you try to make explicit expansion, then it is very complicated. But simply using this kernel function, you can deal with this expansion without explicit expansion. In many cases, this kernel function is not really expressed sometimes it is an infinite dimension. For example, for this Gaussian kernel, if you try to expressly express this one as now phi xi dot phi xj, then in fact this phi function must be in the infinite dimensions, so that you cannot express this one in finite dimensions. But for some cases, the infinite dimensional the expansion can be dealt with quite easily by using this kernel function, so that very rich expansion can be considered by using such kernel function. Here we summarize the linear classifiers and their nonlinear the variants. Perceptrons are simple and popular way to learn a classifier, and then we also consider the Adeline and logistic regression. But these algorithms suffer from inefficient use of data, overfitting, and lack of expressiveness. Now, support vector machines can fix these problems using margins and feature expansion. We try to make the margin as large as possible, and also we try to implicitly use the feature expansion along with the kernel tree into higher dimensional space, so that the algorithm will become more effective. In order to make a feature expansion computationally feasible, we need to kernel trick, which avoids writing out the high dimensional feature vectors. Supported vector machines are popular classifiers because they usually achieve good error rates and can handle unusual type of data sets. Okay. These algorithms are developed by engineers, and looks like they try to find the solutions rather than stuck on the problems. So for yourself, ask what is possible instead of what is wrong. Okay, that's the end of a section. Thank you.